Good afternoon, everyone. On behalf of the Astronomical Society of the University of Colombo, it is my great pleasure to welcome you to today's Astro Talk. This Astro Talk 2.0 session focuses on observation and modeling of binary stars. Today's session highlights the fascinating world of binary star systems and the modern observational techniques and modeling methods used to understand their behavior, structure, and evolution. We are delighted to have you all here for the today's session. It is now my honor to introduce our speaker for the day, Dr. Janaka Adasurya, currently serving as the senior lecturer at the Department of Physics at the University of Colombo. He holds a PhD in astronomy from the University of Colombo and is the first Sri Lankan to hold a PhD in astronomy, and is an expert in the fields of astroseismology, astronomy instrumentation, as well as machine learning applications in astronomy. We are truly privileged to have him with us today. Without further delay, I warmly invite Dr. Janaka Adasurya to deliver his talk.
So thank you very much for the introduction. So I think it is, I'm not new for all of you, right? It is free always actually to talk as well as to discuss during the presentation. Thank you very much for inviting me, and I'm new to the society also. I'm the senior treasurer, right? So I thought maybe it is better to start a talk with myself and then go beyond like Astro Talks with several invited talks. You may actually see some invited talks in future, right, through this session. So let me just go through some aspects of the binary stars. First of all, I have to do a correction that during my introduction, some of you may say that first PhD in Sri Lanka, the first PhD there are a lot of PhD holders in Sri Lanka, Sri Lankan PhD holders in astronomy. The uniqueness is all of them actually taken their PhDs, their PhDs from abroad. So that is the difference, right? So I earned my PhD from here in my soil, right, in Sri Lankan soil and the Sri Lankan University. That is the difference between those PhD holders in astronomy and myself, right? So okay, so let's see about today. I'm going to interact with you some observations and modeling of binary stars. Some of the basics we look at it in the binary stars observations and modeling. The binary stars are a very important part in astronomy, right? Now, when we look at these, I think you can hear me, right? No need the microphone, right? So the binary stars are important in the sense of some parts. There are a lot of objects in astronomy, but when you look at these binary stars, they are actually just providing us a lot of information about the stellar systems, right? Like if you take a single star, it is you can observe a single star, right? But in order to determine the stellar parameters of a single star, it is very difficult. Now let's say, for example, if you go for determination of at least maybe the distance or maybe the mass of a star, it is not going to be easy, right? Because we don't know, especially the distance and the mass, and maybe if you just determine one parameter precisely, then that is the pathway to define or determine the other parameters also, right? So that is how it goes. But if you have like a very, let's say, completely unknown star, so it is very difficult to determine at least the distance to that star. Or maybe let's say the basic parameters like mass, radius, right, temperature, those are really difficult. Especially the mass is very difficult to determine for a star temperature, one way actually it's very easy to get it by through the observations. But in case of sometimes the mass is very difficult to determine, right? So those are some of the problems even for a single star to determine it. But when we go to the binary stars, so the binary stars are very good candidates to go for a parameter estimation, right? Parameters. So the parameters of the let's say the global parameters, temperature, gravity, the mass, radius, and all these things, we can actually determine using binary systems, right? So let's see about how we determine those parameters throughout these slides. So let's go from the beginning, right? At the beginning, let's see how people actually used to observe the binary stars. So I'll start with this presentation in this way: history, and then the introduction of binary stars, and then we discuss about the orbital parameters of binary stars, and the observation, data archives, and modeling. Right. So I just put the data archives. Let's say later on also. So the modeling and data archive both are actually some way very important, or maybe just combined. So therefore, it is very important to learn about the data archives and then hence modeling. So this picture is actually I generated from AI generated picture. So I thought maybe it is always interesting to see these AI generated pictures. So we can't imagine even these pictures, right, to create by ourselves, right? Maybe a very basic picture I had in my mind to put in the background. So, but just produce a nice picture for binary star observation. Okay. So for as an introduction or maybe history, when we just look at these binary stars, how people actually identify binary stars at the beginning, because astronomy is a very old subject, it's the oldest science in the world. So the people used to watch the sky right throughout the time, but they actually observed different objects in the sky, right? So let's look at this, because if you look at the night sky, then you have a lot of stars in between that, right? As well as the close by stars are there, very bright stars are there, very close ones are there, like that. So here, if you look at these two stars, right here, these are right, A and B. So they are very close to each other, right? They are very close to each other. So people think about that. What type of closeness is this, right? It can be, because this is like, it is a 3D picture, right? 3D means we see only 2D, but this is actually came from 3D. So whether we don't know whether how they close, or maybe exactly physically they close, or maybe they are exactly apart, but not physically close because of the line of sight, the vision. So we only get we don't have the depth idea about this, how deep these two objects in the sky, but only in the 2D plane. So therefore, these type of objects we observed, or maybe people observed it a long time back, and they don't know exactly whether they are binary systems, or maybe something physically close by, or maybe not like that, or just to see like in a 2D plane, they are very far, but they are just in a projection in the 2D plane. So therefore, people worried about these things, and these are sometimes identified as actually not as binary stars. So they are called actually double stars, right? Double stars. So they are called double stars because they are very close to each other, not physical. So here, this constellation, I think you are familiar with this constellation. This is Ursa Major, right? Mahavalasa Rashi, right? So in that constellation, we have this Major star, and that is when you look at it very close by, there are two stars adjacent to each other, right? Right. we have a small disturbance in the presentation. Get the presentation now. Yeah, that is better. So those who are actually online, they can see the presentation very clearly. Right. So now here we see that this star is actually, when you look at it through a telescope, then of course the naked eye you don't see that even two stars. So you can see as a one star. So therefore, if you look at it through a telescope, definitely you can see A and B, two stars close to each other. One is brighter than the other one. So then these type of stars, are they binary? Right? That's the question. Are they binary, or maybe they just initially identified these as double stars? Right? They call double stars. They didn't have any idea about they are binary. Binary they didn't have that earlier, right? So they thought maybe they are very close in the sky, so they call that is actually not a binary star, but they call that is a double star, right? So this is a double star in these are the star in the Ursa Major constellation. They are not binary stars. So this binary star concept came little after the historical. The information says that Asian people actually recognize these as like optical doubles, right? As what I showed you earlier. But later on, William Herschel, right? In 19th century, the beginning of the 19th century, 1803, William Herschel coined then the binary star. So he introduced the name of that they are not. They are actually close to each other as well as physically close to each other, right? And then they inform, just name as a binary star because they are always actually bounded to each other by gravity, right? So this idea firstly came out after the William Herschel's observation, and then he was able to publish the first catalog of the binary star with almost 1,000 binary stars. Now we have a big catalog, but this is how people started. And the William Herschel is the first president of the Royal Astronomical Society in UK. Right? He is the president in that society also. Well-known astronomer. So this was the start. And if you look at this, the binary system, now this is a star which is actually responsible for my PhD also. SZ ring, a star, right? So I detailed analyze about this star because this is not only a binary, it is a pulsation as well, but it is a binary as well, right? So this star, when you look at in the night sky, it doesn't actually see like two stars, right? The binary stars, of course, when you just look at it in the night sky, even in a small telescope, you don't see the binary. Right? So that is, I mean, the double stars, of course, you can see, right? They are double, like there are two distinct stars. But the binary stars, usually, you don't see two stars, right? In the sky. So this is a binary star, even that this picture, you don't see two stars close to each other, just a one star, bright star, right? So the binary star is a big, with a period of 3.2 years of period. There are two stars orbiting each other with the 3.2 years of period. Okay. So here the binary star systems to gravitationally bound stars. So we know the definition now. Orbiting common center, they are recognized as a physical pair of by Sir William Herschel in 18th. This discovery allows astronomers to measure the masses and then all the other properties of these binary or the multiple star systems. So we have its animation. It's very simple. can see that. So they can actually move it like this, right? Here, two stars actually moving relative to each other with their common center somewhere here, right? Their orbits. So this is the idea about the binary star system, right? Okay. Then, what are the types of binary stars? So there are different type of binary stars they actually founded. We can classify all the binary stars into more or less in three or four groups exactly, right? So visual binaries, eclipsing binaries, spectroscopic binaries, right? Visual binaries, as it is, the word says, visual binary. That means that some binaries, of course, you can see as two stars, right? The two stars you can identify, maybe not naked eye, but through telescopes, right? When you look at through telescope, you can clearly see there are two companions moving around there, or maybe just one companion going around another star, right? So that is what we call the visual binaries. And then we have eclipsing binaries, spectroscopic binaries. There's another type, actually I did not include here, astrometric binaries, right? Astrometric binaries, but we are not really concerned about, that type. But that is another type, more or less it is close to the visual binary systems, right? Let's see about one by one. Visual binaries. Now if you look at the visual binary, now this is one example that, of course, when they look at through the telescope, right? We can see now it's simpler that again double star, right? So it is confusing whether it is a double star or binary, right? So this is actually a binary system, not a double star, right? So now they observed it in 1908. 1915, 1920. Oh my God, so many years, right? Observation. So it is not close by observation, right? So it is almost like 7 years after that, and then they clearly see that this guy, the small guy, actually just moving or just creeping around the big one, and time to time, while there are some other stars, why these two stars actually shown? Because for the relative motion. To compare it, right? It is shifting across the sky. So we are looking at the same field, but when you look at the same field, because this star is stationary and this small guy is going around with the time. So therefore, we can suspect about this is going to be a binary, not a double star. Because if it is a double star, then the double star cannot be look like that, right? If it is like apart from the background, they have to be always to the same point, right? No relative shift on that. So therefore, we have the visual binary systems, which are both star can be directly separated through the telescope or two distinct points. Now, in this case, this is actually the star is 7 of Punchy, right? I don't know how to pronounce it. Or Pinchy or Punchy, whatever, right? 70, that star, the binary star. And so this type of, all the binaries, you look at it, how they actually move, because they are moving across the center of mass with two orbits. So this is a common explanation about their orbits. So they are going in elliptical orbits. So with their own with their own focus, right? Foci here and then here. So when you look at this binary, right, and that will go across this ellipse, and then this one is goal of this one. And what are the corresponding points of these two binaries? Now, when they come close to each other, like these 2 points, A1 and A2, so the orientation is up. Then the corresponding, the other point like here, B1 and B2, right? And the other 2 points like C1 and C2, the corresponding points. So like that, they orbit around each other, keeping this relationship preserved, right? I mean, we can directly get this relationship for the binary systems. Now, if you take the semi-major axis for the ellipse of this one is A1, and the semi-major axis of the other star is A2. So we can directly relate their masses to their semi-major axis along this equation, right? So when you look at this star, for example, this one, 70 Apache, that it shows that in the time how it moves around the other star, right? Now in this case, most of the time, if sometimes we don't see the orbital movement of this star because maybe this one is a very heavy, right? This one is very heavy. One is very heavy. The other one is lighter compared to that. So usually when you observe it, this one also, now you can see that the center star, the bright one, is almost not moving, right? Maybe there is a slight move, but it is very difficult to detect it, right? The smaller one, you can see clearly going around the other. So this is what they actually just plotted it along the time, right? Maybe several years, because the period is 87.7 years, right? So therefore, we can actually determine the orbit of this star, right? One of the stars of this body compared to the other one, and then we can actually determine this what you call the semi-major axis, right? So we can actually determine the semi-major axis of the ellipse, and therefore we can determine the masses, the mass ratio basically, not the individual masses, but the mass ratio we can determine in one and at least we get some information about the system, right? Not the individual masses in this case, let's say, right? Okay. Further, you can see that now these are actually, the systems, they are not perfect circular orbits. Now, none of these are perfect circular orbits in nature, right? Always we have some eccentricity of these orbits, right? But some cases we can approximate as a circular, but we know that it is not circular. So therefore, when we look at it, the eccentricity of the binary system, so we can see how they look like. Now this is equals 0, no eccentricity, that means circular orbit. So this is the orbital motion, and then equals 0.4, and this is the orbital, let's say the model of the orbit for equals 0.4 eccentricity, here 0.7 and 0.9 highly elliptical orbits. So you can see how they move, right, in the corresponding point. Now always they are moving like this distance, you can see here. Now the semi-major axis of the relative orbits, keeping that is always as A1 plus A2 equals 8, right? The relative orbit. So that means if you just consider that one is relatively stationary, then the other one is going around the object. So then we can determine always the relative semi-major axis as A1 plus A2 is 8, right? And we already know this relationship is holding, right? And then from the two star circulation of the orbit, so we already know the mass of the two stars actually given by this equation, what we call, this is the Newton's version of K plus third law, right? Newton's version of K plus third law. So when you just, because Newton actually came up with the same idea that he also determined the same relationship using the gravitational law. So he came up with the same idea, and is none other than that is a third law, K plus third law. So you can see here, a to the power 3, here we can replace a to the power 3, this is the period, p squared is equal to the addition of the masses plus some constant, right? So we can determine basically if you, because this A1 and A2 we can't measure it, separate, right? We can measure only the relative separation between the two stars. That is possible in the star, right? So if you know, like even the previous image, the relative separation between these two you can determine, even though small. Nowadays we are capable of measuring it with arc seconds of accuracy, right? So therefore we can determine A, and then we let's say we calculate the period of the orbit also, then we have some idea about what are their masses, at least maybe the total mass. Okay? So these are some of the ways we get the information. Basically, we get the information of a binary system. Right, so this is about the visual binary, right? So visually also you can determine some properties of stars using this tool. Let's go for the spectroscopic binaries, right? Some binaries are there, we don't see as a 2-star, right? There's no way of seeing 2 stars as a 2 stars, but just a single star, that's all. But when you take the spectrum of these stars, right, you might be able to see that spectra or the spectral lines are slightly different with the time, right? If you take a time sequence of the spectrum, then the spectra are not same, right? They are different. So how they differ? Of course, you can just assume that because these stars are orbiting around each other, right, in the center of mass. So we get some sort of a Doppler shift, Doppler velocity, right? So one is moving away and the other one is coming towards us. So therefore, in this case, when you look at from this angle, so you will be able to see, you might be able to see 2 spectral lines from two objects, A and B both, right? So the A and B both can give you the 2 spectral lines. But here in this orientation, their radial velocities are actually, let's say, perpendicular to us. So therefore, there is no radial velocity component, and therefore you don't see again no change in the spectral lines. So you see both of them are overlap and then see as a 1 spectral line. So in the other orientation, when you go to the other side, so this AB changes, right, the direction, and again you can see completely different 2 lines, right, and same as here. So this is what you call the spectroscopic binary. You identify the binarity by looking at the spectrum, right? So therefore, they are called binary spectroscopic binaries. So when you look at these are some of the examples, right? Spectra taken from actually Leak Observatory. We have already, we have also some spectra, right? We had some experience about the observation of binary spectroscopic binaries, but I did not include those images because they are really, really weak, right? We can't see 2 lines. I will show you the results, right? We can't see exactly 2 lines over there, but merely just say that, okay, there's a 1 line is clearly there, but we can't see drastically, drastic difference between these 2 lines. But here, you can see clearly this is this orientation, right, taken here, and this orientation or maybe this one. So therefore, there's no splitting, right, here the top frame, and here you can see a splitting, right. Now the line is single, and the next instant the line is double, right, split. Now even you can see that the double nature is always here, all these lines get double, right, split. So therefore it is binary, spectroscopic binary system. You can confirm as a spectroscopic binary system as when you look at these observations, right. Okay, so then it is very important again, the angles in the line of sight, these are orbital parameters, right? Now, here this one is a general case, right? When you look at directly, like if your system is exactly, let's say the orbital plane is exactly aligned with your line of sight, right? So this is the case. So, but that is not the way all the time, right? You have to be always remember that any orientation we will get, right, in space, any orientation, this binary system get any orientation. So therefore, we have to actually consider about the orientation as well in the calculations, right? If you want to get, I think I did not include here. Of course, now when you just get that separation over here, let's say the separation between these two lines from the center line, then what you can actually get? You can get the velocity, right? The radial velocity of the two stars, right? So one is actually just, let's say here, even this diagram, you can actually say that A is the inner orbit, B is the outer orbit. So A is actually moving slower, B is moving faster over here, right? So therefore, you can see here, then the A shifted actually from the central lines less than B. So therefore, the delta lambda, whatever you get, the delta lambda is less for A, and that is more for B. So that means the radial velocity is higher for B and low for A, right? So therefore, even you can actually get the radial velocity of these two stars by measuring how much is the shift. So that is always we can do it. But at the same time, we have to be careful about that. We don't know the orientation of the plane, right? So therefore, it is like just a projection. Now, this the diagram shows that clearly. This is the line of sight, right? The line of sight. Let's say we are looking at this way, but the binary orbit is actually inclined to the line of sight by this angle, I. Actually, we define the angle not with the plane, but with the perpendicular vector to the plane, right? Perpendicular vector to the plane. So here this is the plane, and then the perpendicular vector, the perpendicular orbit of the plane is like this, and then we take the angle with that as I. So that is the usual practice or the rule how we define the plane. So therefore, now let's say the binary is moving like that. So VR is the actual velocity, but we don't get the VR, right? We get only the projection along our side. So it is going to be V sin R, right? Always. So we have to remember that we always actually determine the V sin R, right? Not exactly the true velocity of the orbit. So that is another way of determining what? I. Right? I is also important. That is orbital parameter. Right? How much is he inclined to the our line of sight? That is also important information. So if you really actually, or maybe either you measure V, right? V naught is the actual velocity. Sin I is the angle between the plane. And if you know one of these, either maybe I, you can determine actual speed, or maybe if you know the actual speed, you can go for inclination. Right? So those parameters we can get. Okay, so here, so it is further I explaining. Actually, I taken this image from here, but I just include some more expressions for that image. So this is exactly perpendicular plane to the line of sight. So perpendicular plane means a plane is perpendicular, but your vector is aligned with your direction. So I is going to be 0 in that case. I 0 means this orientation. Right? That means it is perpendicular to that, so we don't have any radial velocity component. Right? All the velocities are perpendicular, no radial velocity component. Right? And the other orientation is this, right? The corner. So then I is going to be 90, and then we don't have that I sin 90 means 1, so then we directly measure whatever the velocity of the star. Okay? So therefore we have to include that when where the I is the angle between the line of sight and the normal object plane. So we have this relationship, right? V1 equals to 5 A1 sin I over B. So A is the semi-major axis of that orbit, I is the equation, and B is the. So we will get some relationship. Let's say we wanted to get some idea about again the mass equation. So we have these relationships. Earlier also I use it. So using these all the relationships, you can find out V1 can be given by this, and you can substitute A from the K plus equation, and then we will get that relationship like this without A, right? Because A is the semi-major axis of the relative orbit even. Sometimes it is difficult to measure it, right? Observationally, that will be very small. So the error is going to be very high. So therefore, we eliminate A, and then we will get an equation with a mass factor. This was a mass function equation. So it is actually only related with the period of the orbit, and velocity is included over here, the radial velocity, and then the mass is also included over here, right? So therefore, when you measure the radial velocity, you can again determine the masses. But if you have, let's say, if you determine the two radial velocities, V1 and V2 both, then we have two equations. So that means we can go for individual masses as well. Earlier we determined on the ratio, but here in the spectroscopic binaries, we can determine two. Yes.
In the case of I equals 0, so there is no Doppler effect in any case.
Yes.
So how can we figure out whether it's a binary system or not?
Yeah, in that case, actually, we can't see any spectroscopic binary nature. There's no way of splitting. We can't identify it, right? Yeah, that's true. Because if it is exactly perpendicular to the line of sight, the plane, we don't see any spectroscopic splitting, right? We can't identify it. I mean, spectroscopic binary means through the observation, we should be able to see two lines. In order to see two lines, at least this should be like a slight angle even, right? When I0, we don't get this, right? So it should have some sort of a component, I component is there to get the two spectroscopic lines, right? And that's why maybe we don't identify this. Maybe there are a lot of binaries, right, like this, but we won't be able to detect it. No way of detecting. So that is a disadvantage, right? In the astronomy, we can't actually detect systems like this, right? Orbiting this. That is in the binary system, as well as you might know about the exoplanet discovery, right? The exoplanets. The exoplanets also discovered in a similar way, right? So it has to be either spectroscopy or maybe a photometry transit method. In order to see this transit or spectroscopic variation, the system has to go with some sort of an inclined plane, and if it is exactly orientation like oriented in that I equals 0 plane, there's no way of detecting. Very difficult. If it is like a visual binary, then of course you can see. Otherwise, these two techniques I'm going to explain about the photometry also, but no way of detecting, right? So that is always there. So, but most of the time, it's very rare cases there, right? But this, even this is very small, right? Even this is very small. So the sin I will give you a very small value of p, right? Small sin I. That means again the velocity component is very small. That means the splitting is very small, right? So that is always challenging, right? We need very powerful instruments to detect it, high resolution spectroscopy to detect it, right? Okay, right. So then you can see here clearly with the orientation, this is like a circular orientation. The nice idea is that we can take it, if it is exactly a circular orientation, those two objects moving in a circle, then we can calculate the radial velocities from point to point with the time to time, right? Because we have a spectroscopic variation, time to time we can calculate the radial velocities and plot it. We can plot the radial velocity curve, right? So when you plot the radial velocity curve for this type of system, so this animation or the picture says clearly it's a pure sine curve, right? the circular pure sine curve. When you look at from this angle, without any angle, right? That is exactly I equals 90, right? I equals 90. So if it is 90, then you can see pure radial velocity curve with sine function like this. The red one is for the inner object, and the other one is blue one is for the outer objects. So the radial velocity is smaller here and then bigger here, but they are symmetrical and pure sine curves. So that information is also you can get it, right? By looking at the radial velocity curve, you can determine what type of system is that, right? Even it is like the angle, of course, you can get it from this idea. Now, for example, let's say if you look at it in this orientation, right? The orbit is eccentric, and you are looking from this angle. So then the two objects actually move it, and the radial velocity will give you something look like this, a skewed radial velocity curve, right? So these are some of the observations where you can see in papers they try to plot and they got different radial velocity patterns, right? So this is the other way, right? When you look at from this orientation, something look like this and then. So therefore, this radial velocity curve is a very important tool, right, to tell about the system, right? So it can also give not only the mass ratios or the individual masses, but it can actually give some idea about the inclination angle, the orientation of the orbit and all, right? So you can see further analysis about this when you look at references. So this is our experience about it long time back, right? The radial velocity curve of the binary system ascent using 45 centimeter Cassidy telescope. We observed it. Actually, the literature says that ascent is a double line spectroscopic binary, right? So it is always recommend confirm that it is a double line spectroscopic binary. But we try to observe it using 45 centimeter, that is almost a half meter telescope with the spectrograph. And what we observed is something look like this. These are the spectral lines, right? And if you spectral lines mean the radial velocity curves, right? Now this is the radial velocity curve for H alpha line, hydrogen alpha line, from the phase from 0 to 5. You can see the phase, right? So the phase is actually I included in the later slide. Shall I go for that for a moment? Yeah, phase is. Yeah, phase is something look like this, right? In the binary phase, I'll just explain it here. The binary phase means binary star. Here we have a primary and secondary. Two components we identify as a primary star and the secondary star, right? When the primary star go across, the primary star actually eclipses by the secondary star. So then that is we call the zero phase. Right? Zero phase here. So the phase 0 start with that when the primary actually covered by the secondary, because that is the major part, what you call the drop, or the most the drop of the light is actually highest at that point, right? Major drop is there. Now the other one is then the primary comes in front of the secondary. That is also covering the secondary, but that is a minor drop, right? The major drop and the minor drop. So therefore, that is just after a half circle. That means phase is 0.5, right? So the point 0 phase, and then when it comes to the primary comes in front of the secondary, then that is called the 0.5 phase, and the other two corners we say that simply 0.25 and 0.7. Right? So that is the phase basically. So we use that phase always, the phase curve, right here. So when you just observe these with the time, and the phase is not really clear, right? Very small, but you can see with the phase. But this is our observation. You can see, but here this is H alpha line. This is a radial velocity shift of the spectra in H alpha from 0.5 to 1 phase, the other half, right? The first half is this one, this is the other half. Now here you can see slightly this with the phase, it is shifting, right? This side goes to this side, tends to move this side, and then they don't go that side. Here also not very clear, but it tends to move this side and then this side, right? So this is how we actually observe. But we don't see clearly two lines. No way of looking at two distinct lines, right? So this is the observation. Further, you can see the H alpha line of that magnified. You can see the phase, and so this. So if you look at this line, this is the theoretical H alpha line, hydrogen alpha line, right? That is a laboratory line. And then when you look at the laboratory line across that, the reference, right? And then this actually shifted towards this side. So this is going to be like the maximum shift is 0.76. See this one. So it is shifted towards the red side. Sorry, towards the blue side. Sorry, red side. Yeah, this is minus. This is plus. So this is blue side. This is the red side. So it is shifted towards the red side, right? At 0.76 maximum here. So that's can be seen. But there are no two lines. Only one peak you can see, right? One peak is. So then this is red and this is blue. So this that. Okay. And the phase is like at this point is 0.76. Maybe it's okay with that the theory what we suppose. And then this is the other set, right? From 0 to 0.5 base, right? Again we can see this is the reference line, and they shifted to this side, blue line. So that is going to be again like 0.27, almost like 0.25. So that means now it is also like a little bit skewed. When you plot the curve, it is not like a perfect sine curve, it is also skewed, right? So we were able to actually plot the radial velocity curve. Don't actually get this one seriously, because this is a very long time back. We produced this one in 2007, right? And this was actually done by undergraduate from Columbia University. She is now at the LIGO program. Maybe you might know her. She is the one actually just connected to the LIGO program, right, in the US. So I guess that she is now no longer there. Maybe she is actually shifted to the radio astronomy. But she did this observation for her undergraduate project in Columbia University, right, from 2007. So these are the observations like the radial velocity curves, right? There are no two components, only one component. And we try to actually determine the radial velocity for here. This is for, I think, H alpha. And we try to observe the secondary component, but not successful, using other lines like aluminium and ferrous lines, but they are very, very weak, and so we are not really get that done, the secondary component. But the primary one component is observed. But this was declared as a double line spectroscopy binary. Our telescope was not really capable of detecting it. The spectrograph and the telescope is not enough, right? So the observation do not clearly give the two spectral lines due to the noise and the resolution. Different techniques can be applied to distinguish them. Yeah, that is a limitation. But though there is a limitation, there are some techniques still you can apply to distinguish these blended lines. Actually, when you look at carefully, this is our observation, right? H alpha line of Sn. Now you can see there is some sort of a tendency to have a now it is asymmetric line, right? So therefore it is tendency to move it this side a little bit more. So you can guess that if it is actually like continuously, or maybe it's permanently there like that shape again and again when you do that observation, So therefore there is some sort of another hidden line within that, blended, right? It's a blended line. Now of course that is the reason, right? The two lines are actually blended because our resolution is not enough to resolve them clearly, but still you can make some techniques, use some techniques to separate them. So here this is the observed line, and then we can clearly just plot a Gaussian fit for this one, and then this side, and then when you combine these two Gaussian lines, you should roughly get the observed line. So there might be some sort of a way to get that idea about the secondary component as well. That's a very simple technique, like a blending of the line profile. So we try to do that, and that's where we actually determine the secondary component for the others, some of the other lines. But you know, there are some problems with the H alpha, because H alpha is a very highly broad line, right? It's a broad line. Hydrogen lines are very broad, so they are not the good ones to determine this type of observation, right? Hydrogen lines are very broad. There are a lot of broadening effects actually come with the hydrogen. Thermal broadening, rotation broadening, Doppler broadening and all, right? So it is better to look at metallic lines, right? Metallic lines. So if you go for the metallic lines like ferrous, maybe something like a magnesium or something, so it is better because there's no broadening or less broad. So you can see a sharp line. Whatever happens to that line splitting, that can be actually then detected. Hydrogen is the worst case, right? But hydrogen is the clearly available line in the spectroscopic observation, right? There are some positives and negatives, right? So this is another technique. We also tried it. Now there are some few techniques. There are a lot of techniques when you look at the research papers, right? That is how they do the research, right? So they always try to maximize these the detection. So this is actually what we call the broadening function and the cross-correlation function. The cross-correlation function is the one we can use it usually, but this is a new function, not new now, because this one was introduced very long time back, but still you can use it. Now these are two images, two spectra. This one is a usual star, right? Not a binary, but this one is a binary, right? So when you just look at this one, this is a magnesium line, magnesium triplet. There's a magnesium like sodium doublet. We have magnesium triplets like that, triplets, doublets. Right? So here these three lines actually show strong lines. They are magnesium triplet. Three lines, magnesium line. Now this magnesium line actually here get broad. See, right? Here for this one for the binary, this one for the usual star. The magnesium available on those both. But when you look at these two and then combine these two and then get the cross-correlation function, you should be able to identify the separate, or maybe the what you call the different peaks with this line. The peaks means something like a broad cases in this line. So this is what you call the cross-correlation function, right? Of these all three, like if you apply the cross-correlation, so you should be able to see some here a jump, or maybe just a hump, and then there's another big one, and there's another hump. So it is not clear, right? Even not clearly seen, not separated. But when you look at another technique called the broadening function, so that function, when you applied it, these three lines actually show separately, clearly three lines, and then you added up the total broadening function. Broadening function. So then the total broadening function is something look like this in this case. But it is better than the cross-correlation function. So you can see here another hump over here, and then clearly there's another one, peak, and there's another one. But these are something like how do we improve, right? Different techniques to improve the detection. How to discover the available information, the hidden information in these observations, right? With the time I will go right quickly because so the photometric then we'll just go for the photometric binary stars. So the photometric binary stars means we measure the light, the blocking of light when one is going in front of the other. So therefore you can see the photometric or eclipsing binary stars. So that is another type of binary we can go for observations and then find out this. So this is how it works, right? Animation. So that will give you again with a phase a primary and the secondary component, right? Here we have the primary component and the secondary component. So like that, light curve measurements, right? Okay. So when you look at the light curve measurements, it also gives a lot of information about this binary system. For example, this is one example for Algol type binary. Algol type binary. So what do you mean by this Algol type binary? Means a binary, two binary stars are well separated, right? They are well separated, not close to each other. So therefore we have the primary and secondary component are there, but most of the light curve is flat. Most of the light curve is flat. So that type of light curves we call Algol type light curves, Algol systems. Now for the next one, beta Lyrae type. Now here they are very close to each other, right? Almost detached by, almost combined them, but separated. So then those type of binary system will give you something look like this, right? But here still you can see. Now here it is very clearly see that the primary and the secondary is very weak, primary is very strong. But here you can see the primary and secondary are also actually very clearly distinguished, right? While that the flat part is not that much of long or bigger compared to the Algol, so it is like very close to each other, right? Then we have the other. Now these are primary eclipses, right? And then the secondary eclipses. Then we have W Uma type, that means actually not detached, combined, right? They are attached to each other almost. So then you will be able to see something look like there's no flat component at all, but primary and secondary, even the secondary is very close to the primary in magnitude, right? Secondary is also close to the magnitude of the primary. So those are some of the different type of light curves. We can get the primary idea about whatever the system, like it is a Algol type system, or maybe a beta Lyrae type, or maybe W1 type, right? Depending on the line. So this is again the phase curve. You can see this is a Algol type. You can see the flat part here. Flat part is over here. So this is with the phase, right? Phase 0, phase 1. 0 means here primary is eclipsing, so therefore primary eclipse, secondary eclipse. And this is one beta Lyrae type. You can see the flat part is reduced and the secondary is primary and clearly distinguished. But this one, sometimes you don't see the distinguish of secondary and primary when they are almost close to each other, and there's no way of looking at this flat part. So they are very close attached binaries, right? Now our experience about this observation or modeling of eclipsing binaries. Of course, you can get the observation using Kepler or maybe TESS or whatever. There are a lot of light curves available for these binaries. You could go for Kepler and TESS. Right? No need to wait. If you want to do research, then the data is available very much, right? Everywhere. So the Kepler data, we use it, and we use the modeling code for the Wilson and Debye code, WD code, right? What we can do here is we can model the light curve using this code, right? So you can see the black, of course, is already covered by the red line. Black means observation data, black, right? And the red line is the model using the code. So these are 4 stars, right? K plus stars you can see here. Their names also given here. So this is actually as a result of my PhD students working on it now. We got this results from that study. So 4 stars. Now, so you can see some of them are like algoritide, right? Some of them are beta lyrate, and some of them are like W, right? So here it is very clear this is an algoritide, right? The flat part is there here. But here this one is like, but you can see the primary and secondary clearly. This is going to be a beta lyrate type, right? But not the other one, because always we can see clearly the primary and secondary. So either alcohol or beta lyrate. The downline actually, the plot is the residual, right? The residual of this. Actually we did this one for different purpose, but binary analysis we did it at the beginning, but we go for another analysis later on. So that's the case. So when you just, what is the purpose of doing this modeling? Now let's say you have a observation data, we don't have any idea about the binary system, we don't have any idea about, right? Maybe initial parameters, we can guess it like temperature and all these things, we can feed it to the modeling and then we can initiate it, but then if it is not clearly close to that observation, we can fine tune the parameters and then finally we can exactly match with the observations, right? So when you match with the observations, you have a parameter set, right? So that is the parameters of what? The binary system. So that way you can determine all these parameters like temperature, mass, radius, log g, right? Luminosity, inclination angle and everything. You can get some idea about for unknown system in that case, right? You can approximate it. So that's what we did. So this is our study for that particular star, and this is actually the same star actually done in earlier also. Some changes because we actually did it in another way. We go for a rigorous analysis of this star using WD code. There are different codes. This is a WD and this is another code, COBE, right? COBE. So these are the models, physical models of the WD code for KIC star. You can see this, the fit, right? And these are also you can actually produce using the same code. I mean, they can animate the binary nature of these two. You can clearly see these two are detached binary, right? This is a detached binary, well detached binary, and sometimes using these light curves have some drops there, right? Here, some differences over here. So that will actually predict that, I mean, we are not confirmed about this one, right? We have to be very careful about that. There are some star spots, right? Like sunspots, right? If it is like a big spot in the star, so that will also give some sort of a dimming, right? Nature, dimming effect of the light curve. So those type of dimming effect might be there slightly, right? When you fit it, the fit can actually identify it is going to be like a periodic, and then it can predict it some kind of effect. So maybe some third object, right? We don't know. Another maybe object, not a binary, maybe a triplet, right? Triple star system, or maybe a small guy, right? Covering it. Don't know. Maybe a star spot, a big one. So these are like, when we do the modeling, and the model actually proposed that there should be some sort of a spot over here, you can see, and that spot is actually just sometimes it is actually directing towards us more, sometimes otherwise, right? So it will also give some idea about it, and there are a lot of things to find it out, right, from the light curve. So this is another one, and this is also well detached. You can see how well detached because this is a flat, and then you can see the separation, the model. Okay, so those are some of the things actually I just wanted to share with you because time is also gone. But these are some of the ways actually we do the binary star modeling and observation. Always we do observation. That is also important. Without observation we can't do anything. But the observations are available, the light curves are available. Spectroscopic data is bit difficult to find it out. It is not available freely, but spectroscopic photometry data is available, right? You can do always this photometric observation and modeling. I mean, wherever you want to for research or something like that, right? So that is always available, and find it out information about it. And these are some of the data sets that in paper test working you are familiar. The WD code you can get it from here, and the POBE is another code. But my experience is POBE is the WD code is a rigorous code with lot of facilities. We run actually two light curve modelings like LC mode and the DC mode. The DC mode actually refined again and again several times. You can actually run more iterations in a differential mode, right? So then you can refine again the data. That's what we found. Sometimes most of the people actually done the LC mode, light curve modeling only. But the differential the modeling they haven't done. So we perform the differential modeling and then find out. Even we can go for a fine modeling of the light curves and then get different type of the data, like the parameters. You can see the temperatures might be slightly different, right? So you can fine tune, right? And that may be important for next step. What is called the stellar modeling. Stellar modeling means we use that same set of parameters for another model. So it is a parameter dependent. If your parameter set has a high error, right, then the modeling is also errors, right? There are a lot of errors in there. So therefore, it is very important to define or maybe a good set of parameters with a very high accuracy, right? So that is also encouraging to do that. So that's what we did. WD code and the POBE. POBE is another code, but I don't know about it because anyway, there's another student working with me. She is actually working with the POBE, right? So we can compare it later on. So, however, we have both experience right now. WD code is actually that is the very old code, the first code, right? Listen and they will code. There are a lot of binary models, but these are well-known codes. If you want to actually do research, these are available at every time, right? Free, open source codes. Right? Okay, so that's all about my talk. I think you get some idea about what we can do in research, observation and research. If you are really like to do for research, the data is available, the codes are free, so you have to work with that. Okay, start working on it. Okay, so thank you very much. If you have any question, I'd like to. Yes, yes. Yes, exactly. The truth, right? So I did not actually just explain about those things. Now, this is just a binary observation. But when you get some data set, you have to be very careful about. There are a lot of predictions that have to be made, right? One thing that's what I say that the orbital motion of the Earth, right? So we are actually we are always going on, right, in space. So then when we actually get some observation, our speed of Earth, 30 kilometers per second, they are moving 30 kilometers per second around the sun. So 30 kilometers per second means it is always actually affected to these observations, right? Radial velocity. So that has to be corrected, right? So that has to be considered. That is called heliocentric correction. Heliocentric means we correct it we finally bring it or shifted it to the sun center, right? Heliocentric correction. So there are a lot of things I have included the correction wise, right? Everything what we do, spectroscopy, photometry and everything, so we have to do this basic corrections. Heliocentric correction means we eliminate the movement of the earth and then we just transform the observations to the center of the sun. Don't ask me that the center of the sun is also moving, right? Across the galaxy, right? So, but anyway, if you are going to go for that much of accuracy to determine something very accurate, that also has to be corrected. But we are not really worried about that speed where the sun and the entire solar system actually moving across the galaxy. And the other thing is, now here, that the binary system sometimes, the entire system is also moving, right? While it is orbiting around each other, the entire system has a translational velocity, translational movement. So that will also within that observation. That's why when you observe it, sometimes you don't see a clear cut of moving towards red side or blue side. Sometimes it is actually moving towards red side and it's not really shown that it is crossing the reference line, but it is shifted to the blue side slightly. Why? Because we have translational motion. That means observed line, we are not really looking at that line, but slightly a moved reference frame. That reference frame actually moved means that observed line is not exactly along the reference line of HR, slightly away from that, right? So those are the things we have to be very careful about when we do research. Right? All the corrections has to be made. Otherwise, you are actually end up with some, kind of, okay, if you determine the velocity like without those corrections, your masses will end up with a different values, right? So those are always actually have to be careful about it. Right? A lot of corrections has to be made for you to the conclusion. So that's very important, right? So those are there. We have to aware about that. Even you know that these Kepler, right? The Kepler tests, they are also observatories, space-based observatories. They are also moving, right? Why? None of them are like static field, right? They are also moving. So there are some orbital movement of these Kepler and test missions. So we have to be consider about that also, right? So those now when you read the research papers, so you can find it out how people actually just consider about all these aspects and then eliminate all these effects getting done with the 100% accurate. Yeah, I'm not sure about 100% accurate, but at least we have to count all these known things or the effects to our calculations. So that's even sometimes it is like a headache to think about all these things at once. But that is how the research papers actually going on, right? They are very concerned about these things. Otherwise, you don't actually get published it. So when the paper actually just put into that referees, so they ask about everything. If you consider this, right? If you don't say that no, that is wrong, right? So those are the things. Right. So that's about it. Think there are any other questions? If not, we can.
Thank you very much, sir, for that insightful and impactful presentation. Now, I would like to invite the President of the Astronomical Society of the University of Colombo, Mr. Kamidu Amarasinghe, on stage to present Dr. Janaka Adasuri with a talk on a capstone.
Thank you very much anyway. So anyway, I think we can go for a series of talks, right? I think planning for that. So I guess that we will get more invitees. Professor Chandra Vikram Singh is engaged right now. So we